Everybody is welcome to my YouTube channel. Today I want to discuss on the topics of AVL Tree. And previous my video I discussed on binary tree, B tree, and binary stars tree. Now I want to discuss on the topics of AVL tree. AVL tree also a type of binary tree and also binary stars tree, and they have some property of the AVL tree. That is, each and every node of the AVL tree have a balance factor, and this balance factor will be their balance factor have a limitation within the value of 0, 1, plus 0, 1, 0, minus 1. This is the parameter, this is the limitation of the balance factor. And each and every node will take the value of the node as per binary size tree, like the binary stars tree. So now we want what is the insertion process of the AVL tree. Suppose this is a node 50. So this is another node 40. This is the right child of 50. Suppose 60. So we have to calculate the balance factor. Balance factor of 40 is left child balance factor BF equal to number of left child minus number of right child. Number of left child minus number of right child, that is here number of left child 0, number of right child 0. So 0 minus 0, that is 0. At that point same 0. At that point 1 minus 1, that is 0. So the tree showing the perfect balance tree of the AVL tree. So this is a AVL tree, not only binary search tree but also AVL tree. If we add another node, suppose left child of 40, 38. I am calculating the balance factor. Balance factor 38, 0. At that point 1 minus 0, that is 1. At that point 2 minus 1. Sorry, this node consists no children. So balance factor 0. At that point balance factor is 2 minus 1. That is 2 minus 1. That is 1. So balance factor is already checked and it is under condition. So it is a AVL tree. Not only binary search tree but also AVL tree. Now I am inserting another node. Suppose 40, left side of 40, 42. Now I am checking the balance factor. 42 balance factor 0. 40 balance factor 1 minus 1, that is 0. 1 minus 1, that is called 0. The balance factor of 50, 2 minus 1, that is 1. Balance factor of 60, 0. So till now it is exactly an AVL tree. The balance factor is within the 2, not greater than 2, and not equal to also 2. Now we are adding another node, that is 42, right child of 42, 43. Now I am checking balance factor 43 is 0, balance factor 42 is 1, 40 balance factor 1, 2 minus 1, 2 minus 1, that is 2 minus 1, that is 1. Balance factor 50, 1, 2, 3 minus 1, 3 minus 1, that is 3 minus 1, that is 2. Balance factor of 60 is 0. So at that point it is losing the balance at the point 50. So it is not AVL tree, it is a binary search tree only. And now we have to convert this tree at AVL tree by rotation. This balance is lost its balance due to this inserting this node. So we have to take a 3 node. Suppose 50, 50, 40 to 42. So I am taking the 3 nodes, only 3 nodes. 50, 40, 42. 50, 42, this balance factor is 0, this balance factor is 0 minus 1, that is minus 1, this balance factor of this 50 is 2 minus 0, that is 2. So to remove this balance factor, you have to make normal of the balance factor of 50. How this normalization will be occurred? Now, so this is a case of right left rotation. This rotation, and we have to move the rotation as per rules of RL. What is the RL rules? Rules is at this point it will move left twice. This is right child, so moving will be left twice. So 42 will take at the place of 40, and 40 will go at that point. So 42 will be removed, 42 will come at that point, and 42 will go here. And this is the left to right movement. Another movement is required, that is left to right movement. The 40 in this movement, 42 will be at the center point. 42, 50, and 40. This is the final movement, and at this movement the T is normalized, and now it is AVL Tree. If we check the BF, 40 BF 0, 40, 50 BF 0, 42 BF 1 minus 1 0. So it is now normal. It is a AVL Tree. So already we have shown the one rotation RL. Now I am showing another rotation, that is LR, LL, and RR. RR rotation. Right rotation. Two nodes at one is right child of another. Suppose this is 50, this is 51, this is 52. This is RR rotation. The balance factor of this each case 0, that is 0 minus 1 minus 1, that is minus 2. So movement will be in these cases. 51 will come at that point, 50 will go at left child of 51, 52 will take the right position of 50. If we calculate BF 50 0, 52 0, 51 1 minus 1, that is 0. So this is called RR movement, right movement. Okay. Now I am coming LL rotation. LL. This is one node, this is another node, this is another node. All is this node, left child, this is the left child of this node, this is the left child of this node. So right movement is required. Suppose this is 50, this is 44, this is 42. The movement will be in this point. 44, 50, 42. This is the final position of this is the LL rotation, left rotation. If we check BF 0, BF 0, 1 minus 1, that is 0. So LL rotation is called LL rotation. RL rotation, already I have shown the RL rotation. Now please see again RL rotation. R means right, left. 0 node. Suppose this is 50, right side 51, left, sorry, 55, suppose 54. Now if we check the balance factor, then 0. If balance factor is 1 minus 0, that is 1. It had 0 minus 2, that is minus 2. Now see the balance factor here minus 2. So it is not a AVL tree, it is imbalanced tree. That is called only binary search tree. Now we have to move, make rotation. We have to make the rotation. Rotation means this rotation will be as per right direction. So 54 will go at that point, 55 will come here. 54 will take at the place of 55. 54. This will be removed. Okay. So after is this one movement, another movement is 54 will take turn as left turn, and then 54, 50, center point 54, 55 at the right child of 54. If we count balance factor 0, balance factor 1 minus 1, 0, this is 0. So two movement. This is RL movement. We have already shown RL movement. Now I am coming to another movement, that is LR movement. LR, left, right. Note 1, note 2, note 3. Suppose this note 50 less 40, 40 less 42. Sorry, 32. Now this is, sorry, LR, not LL. LR, that is L left, R right side. Suppose 44. Okay. Now first movement will be this way. That is 40 will go at a left, at lower portion. 44 will take at that portion of 40. 44 will be vanished, and 44 will go at upwards, and in the place of 40 and 40. Okay, 44, 40, and 50. Okay. Now the next movement will be in this one. 44 at the center point, 50 at that point, and 40 at this point. So this is the final movement of LR movement, left, right movement. So four rotation. Already I have shown the four rotation of the AVL tree. By rotation, we are converting the imbalance condition of the tree at normal position. So it is a four rotation of the AVL tree is existing. If we see the comparison figure, that is, if we see the set, if consider this set is the full of binary tree. Now, binary search tree will be like this. BST, binary search tree, will be like this. If want to see AVL tree will be like this set. AVL tree, so all binary tree are not AVL tree. But if all AVL tree is also binary tree. All BST also binary tree. And all AVL also binary trees. But all are binary tree is not AVL tree or BST tree. This is the small set that we can show that the relation between the three T. Now, if we want to insert the value, suppose 50, 40, 41, 39 to 0. I want to put the value following values at the AVL tree. Suppose 50, 50. 40 is less than 50, 40. 41 greater than 50, less than 50, greater than 41. That is 41. Each and every insertion I have to check the balance factor. So if we check the balance factor 41, then 0. Balance factor 40 left minus right, minus 1. Balance factor 50 is 2 minus 0, 2. So at that point 50, there is no balance as per like AVL tree. So we have to remove this 2, and it should be between 1, minus 1, or 0. So the rotation is required. What type of rotation is required? First rotation left to right, second rotation right to left. At this rotation, the point is 41 will take the position of 40, 40 will be removed, 41 will come here, and 40 will go at that position. Rotation like this. Okay. After one rotation, this is the value. Next rotation, 41 will take middle position, center position, 41, and the right child 50, and left child 40. So after inserting three values, only three values, we have shown this is the figure of AVL tree. Now, next 39. 39 less than 40, 39 less than 40. Okay. Now we have to check the balance figure. 39, balance factor 0. 40 balance factor 1 minus 0, that is 1. 41 balance factor 2 minus 1, that is 1. 50 balance factor 0. Now I'm inserting next node 20. 20 is less than 39. Okay. So balance factor 20 is 0. Balance factor 39 is 1. Balance factor 40 is 2. Now we are coming to another problem, that is 2. But at that point, 3 minus 1, that is 2. So at that point, we are losing the balance. That is at point of 40. So movement is required. What type of movement is required? LL movement. Now I am shifting the value 40 here, 39. LL movement. That is right movement. 39, 40, and 20. So after 49 will come 39. It will be removed and new set will appear here, 39, 40, 20. So this is the movement. If we see the balance, 20 is less than 39, left position, 40 is greater than 39, right positions, 41 greater than 39, upper position, and 40, 50 is greater than 41, this is the lower position, right position of the 41. So this is the figure after converting of the by 4 notation, RR, LL, RL, and LR. So this is the end of the video, and I am already shown the T, binary tree, B tree, binary search tree, and also AVL tree. Thank you, everybody.